Hello again. This is Math 2233 coming to you from the College of DuPage. And the title of this lecture is The Multivariable Chain Rule. As always, please be an active learner as you watch these videos. Let's begin by recalling that the chain rule for functions of a single variable gave us a rule for differentiating composite functions. So if y is equal to f of x, but x was also equal to g of t, where f and g were differentiable functions, then y is a differentiable function of t, and the derivative of y with respect to t is the derivative of y with respect to x times the derivative of x with respect to t. For functions of more than one variable, the chain rule has several versions, each of which giving a different rule, conceptually the same, but a different rule for differentiating the composite functions. And so we'll look at these multiple versions, and we'll start with the case where z is equal to f of xy, and each of the variables x and y is in turn a function of the variable t. This means that z is indirectly a function of t through the composite functions, and z is equal to f evaluated at g of t comma h of t. And the chain rule will give us a formula for differentiating z as a function of t. This will be a normal derivative dz dt. And throughout, we're going to assume that f is differentiable, and that's going to be the case whenever the partials with respect to x and y are continuous. So here is our first version of the chain rule. Suppose that z is equal to f of xy is a differentiable function of x and y, and x is equal to g of t and y is equal to h of t are also both differentiable functions of t. Then z itself, this one, is a differentiable function of t, and the ordinary derivative of z with respect to t is the partial of f with respect to x times the ordinary derivative of x with respect to t plus the partial of f with respect to y times the ordinary derivative of y with respect to t. Now it's instructive to look at the proof of this, so let's do it. And so recall that a change in of delta t in t produces a change delta z, delta x in x, and delta y in y, and that makes a change in z. And previously we talked about this, that delta z is equal to the partial with respect to x times delta x, the partial with respect to y times delta y, and epsilon times delta x, and epsilon 2 times delta y. And where both those epsilons go to 0 as delta x, delta y goes to 0, 0. So what we can do is we can divide all the way through by delta t of this equation, getting this. Now notice that when we take delta y over delta t, delta x over delta t, delta y over delta t, and delta x over delta t, in the limit those are going to be equal to 0. So now we let the limit delta t go to 0. And we are using the fact that delta x is equal to g of t plus delta t minus g of t, and that goes to 0 because g is differentiable and therefore continuous, and similarly delta y goes to 0. So this in turn means that epsilon 1 goes to 0 and epsilon 2 goes to 0. So when we take that limit, then we can take the limit of delta t, and this is a constant with respect to delta t, as this one is, and we're taking the limit as delta t goes to 0. These are going to 0. And so what we find is that this in the limit then is going to be what we were trying to prove. So dz dt, the normal derivative, is equal to the partial of f with respect to z, partial of f with respect to x times dx dt, partial of f with respect to y times dy dt. And there's the proof. Now, since we often write the partial of z with respect to x in place of the partial of f with respect to x, we could write the formula just in terms of z's, and note the similarity of this to the differential formula that we've studied before about the total differential. It all hangs together and all makes sense. Let's do a problem. So here we have if z is equal to x squared y plus 3xy to the fourth, but x is in turn equal to sine of 2t and y is equal to cosine of 2t. We want to find the derivative of z with respect to t when t is equal to 0. You know what to do. Let's see how you did. Okay, well, this is the chain rule that we have. dz dt is the partial of z with respect to x times dx dt plus partial of z with respect to y times dy dt. So y is equal to the derivative of y with respect to t is minus sine of t, and the derivative of x with respect to t is 2 cosine times 2 cosine of 2 cosine of 2t, and the partial of z with respect to x is going to be 2xy plus 3y to the fourth, and the partial of z with respect to y is going to simply be x squared plus 12xy cubed. And so we have this, and we then substitute these values in when t is equal to 0. And when t is equal to 0, we know that x is 0 and y is 1. And so we substitute all those numbers in, and we get that the value of this derivative is 6 when t is equal to 0. Now, the derivative that we just thought about was really a function of, it was in three-dimensional space. It can be interpreted as the rate of change of z, and you can think of that as a third axis coming out towards you if you want, with respect to t at the point xy. As xy moves along this curve, and this curve is the parametric curve, x is equal to sine of 2t, y is equal to cosine of t. And so in particular, at t equals 0, what we have is this is at the point 0, 1, and the derivative was 6 is the rate of change through that point. So for instance, if t of xy was equal to this is the temperature at a point, then the composite function represents the temperature along that curve, and the derivative corresponds to the rate at which it changes. Let's look at another example. Suppose that the pressure P in kilopascals, and a pascal is a Newton per square meter. The volume is in liters, and the temperature is in, it could be Celsius, but here we're taking it in kelvins, of a mole of an ideal gas is related to this by this equation. This is the ideal gas law. So the pressure times the volume is equal to, I think this is in our, actually let's don't play all the chemistry, but pressure times volume is equal to 8.31 T. So we want to find the rate of change at which the pressure is changing when the temperature is 300 Kelvin and it's increasing at a rate of 0.1 degrees Kelvin per second, and the volume is 100 liters and is increasing at a rate of 0.2 liters per second. Now, this is going to be the partial with respect to time, of course. So what we're trying to find is that, and we're going to have to use partial derivatives and the chain rule. Okay, so you know what to do. Let's see how you did. Okay, so we're going to solve for P, and we get 8.1 T over V, and now we're going to do the chain rule. Now realize that both of these things are functions of T. So the derivative of P with respect to T is going to be the partial of P with respect to T times the derivative of T, capital T, with respect to time. That's the derivative of temperature with respect to time, plus the partial with respect to V times dV dt. So this is going to be the partial with respect to t is just going to be 1 over v dv dt, and then we have that constant 8.31 there, and then we're taking the derivative here with respect to v, but that's 1 over v, so that's going to be minus 1 over v squared. The t is held constant, dv dt. So we have this, we substitute all those values in and do the calculation. It's a numerical calculation, and we find that the pressure is decreasing at a rate of about 0.42 kilopascals per second. Now we're going to turn to considering a situation where z is equal to f of xy, but each of x and y is a function of not one variable but two variables, and this is going to be s of t. So x is going to be g of s and t, and y is going to be h of s and t. So z is indirectly a function of both s and t. And now we're not going to have regular derivatives, we're going to have partial derivatives, and we want to find the partial of z with respect to s and the partial of z with respect to t. Well, recall that when we computed these partials, we held s fixed when we're going with respect to t, and computed an ordinary derivative of x with respect to t. So we're going to apply that theorem here, and we will find this result. So the partial of we found this result previously. So the partial of z with respect to t is the partial of z with respect to x times the partial of x with respect to t, and this is this is the partial of z with respect to y times the partial of y with respect to t. And a similar argument could hold for the partial of z with respect to x. So we've really proven this version of the chain rule. So suppose that z equals f of xy is a differentiable function of x and y are in turn given by g of st and h of st, respectively, where those are differentiable functions of st. Then the partial of z with respect to s is the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y times the partial of y with respect to z. And similarly, the partial of z with respect to t is the partial of z with respect to x times the partial of x with respect to t, plus the partial of y with respect to partial of z with respect to y times the partial of y with respect to t. Now, if that seems like a lot to remember, it really is. And so my Calc 3 teacher, who was a gentleman by the name of Andre de Corbin, who was a fine mathematician, his PhD was from UCLA in mathematics, but he was born in Berlin from Russian parents and was educated in France. He spoke German, Russian, and French. I actually thought he was a Frenchman at the time. He had more hair, and his hair was blacker then, but he looked much the same. Other than that, I've since learned that he did a lot of collaborative research in mathematics, but additionally turned and was doing research in computer science, and he was a professor of computer science at other schools, and he also is published 4 volumes of poetry. Quite a guy, Andre de Corbin. And Andre did not talk about the title of this lecture being the chain rule. He talked about this lecture being called trees. So you see, what we do is we draw a tree, and that helps us remember the chain rule. So you see, z is a function of x and y, and x and y are functions of s and t, s and t. So to find the derivative with respect to s, we go along here, and along here, and along here, and along here. So the partial of z with respect to s is going to be the product of these two plus the product of these two. Similarly, using the tree, the partial of z with respect to t is going to be going down this product, and it's going to go down this branch of the tree. And these are the formulas that we get. And Andre also could use those writing it this way too, and we could even have something more complicated. But let's do a real example of this. Here we got s and t again. So here what we're going to do is we're going to use the chain rule to find the partial of z with respect to s and the partial of z with respect to t, where z is this function, x is this function, and y is this function. So the partial of z with respect to s is we're going to go down this branch and then down this branch, plus we're going to go down this branch and this branch. So you see he does all of that, and so here we're going to have the partial of z with respect to x is going to be 2xy cubed, and the partial of x with respect to s is cosine of t, plus this other branch is going to be the partial of z with respect to y, which is going to be 3x squared y squared, and the partial of y with respect to s is going to be the sine of t. And similarly, down the other branch, and we're going to find that the partial of z with respect to t is going to be minus 2sx y cubed sine of t plus 3s x squared y squared cosine of t. Make sure you understand this example. And if we were asking to find this problem, then u is equal to x squared plus yz. X was rs cosine of t, y is rs sine of t, and z is r plus s. And we wanted to find and see u as a function of 3 variables. We again draw a tree. Now we don't have to show all those parcels, but we say u is a function of x, y, and z. And each of x, y, and z are in turn functions of r, s, and t, r, s, and t. So what we're asking you to do here is find the partial of u with respect to s when r is 2, s is 3, and t is 0. Well, we're going to go down this way. We're finding the partial with respect to s, so we go down here, and then we do this one. We're going to go down here and do that one, and we're going to go down here and do this one. And so this is the partial differential equation that we end up with. And we do the calculations, and we will get 2xr cosine of t plus zr sine of t plus y. And then we plug in the values 2, 3, and 0, and we will get that this number is 24. Again, make certain that you understand these calculations. In closing, now more than ever, time is precious. Each day must count. Do the math that will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all, and we'll see you in the continuation of this lecture.